Research for the past 4 years has been the use of sonification in astronomy. Now, that might sound a bit abstract. So what do we mean? Why would sonification, first of all, is known as the use of sound which is non-verbal, so it's not using words, to represent data. Now, why would you use sound to represent data? So sound itself is very good for recognizing temporal phenomena around us. Now, how is this possible? Through sound, we can hear rhythm. So we know this when we hear the ticking of a clock, for example, we can hear the seconds. We know this as well from walking, from footsteps, whether a person is walking slowly, moderately, fast, somebody's running. We can hear the distance of a person and calculate whether they're far or they're coming closer. So a very simple example would be if you listen to a siren of an ambulance. If you hear it from a distance, it doesn't sound clear. The loudness is low, and something called the pitch is slightly low as well. And as the ambulance comes closer, what happens is the volume or the loudness becomes louder, the sound becomes clearer, and you hear that the siren is becoming higher in terms of notes or in pitch. So it approaches us, it passes us, and as it moves away from us, the loudness starts to reduce again, the clarity of the signal starts to reduce, and the so-called pitch, or the notes, if you look at it from musical term, they start to decrease as well. So that is the way that we can measure the environment. So what we're doing all the time is that we're literally analyzing the environment and measuring it and collecting a lot of data. So we're collecting between 20 times per second to 20,000 times per second of data. That's really fast. And because of the way that our ears are connected to our brain neurologically, that signal is processed in such a fast speed that we can immediately associate sounds. Let's think of an example that when mankind or humanity was still in the stage of being hunters. Let's say you were hunting in a dense jungle or some kind of place where you couldn't always see what was going on. Now, don't forget, you're hunting, but you're also being hunted. So you can't always see, but your ears allow you to perceive whether something is moving, whether something is moving away from you, whether it's moving towards you, whether it's happening on the left of you, on the right of you, and whether something is approaching fast or leaving at a fast rate. So this is the way that we can perceive the world without using our eyes. Now, we come from a very visual dependent society where we use our eyes a lot for a lot of things. But the whole idea behind this research is, what if we use these skills that we use in everyday life to interpret our environment and use our ears instead to interpret data? So this is basically why sound could be a very effective method of representing data.
And it is so spontaneous that you don't even realize how much information you're actually managing and transforming. Because when you're talking about all these examples, they're everyday examples, they're very clear. And you think, well, yeah, there's so much information, and I don't know how many processes my brain doing in order to transform all these sound waves, in order to transform the amplitude in order to transfer the volume, the pitch into useful information for my survival. When you were talking about prehistorical men, and even today, you need to know if your wife is mad at you or if she's happy, and you know those things because of the pitch and because of the altitude, etc. And it's funny you say that, yes, we do live in a very visual society, but I was not thinking, well, is this a narrative? Are we really that visual, or we just live in a world where, well, technology and the way we engage into societal relationships, it's more visual, but we are actually highly auditive. That just makes me think about it.
Yeah, I think it really depends on the way that we're actually doing data analysis currently. And we tend to depend mainly on graphs, visual graphs, or visualization representations, numerical representations. So this is it. It's like in our everyday life, we are extremely auditory. So if we put the element of survival into today's world, simple survival is crossing the road. So hearing the engine speed, we can tell whether the engine is becoming faster or slower. And we're so good at doing that because we've been doing that from such a young age that we can tell whether it's safe or not to cross. And usually we don't really look, we just glimpse very quickly, but we're depending a lot on our ears to give us that information, whether a car is actually far away or not. So apart from the temporal, you see, this is where the temporal aspect really comes in, the whole idea of time and space. So I think when it comes to the auditory realm, time and space really have to be looked at as one thing rather than separate things. And the whole reason for I'm saying this is because if you're in a particular environment where you have, let's say in a cityscape where you have a number of different sounds, happening all at once, we have the ability to choose which sounds we want to listen to. So we can actually separate this and say, right, we want to listen to this and listen to that. Maybe with auditory, the auditory sense, there is a certain advantage where if you get two different colors and you merge them together, they create a new color. But with sound, and we hear this in music, if you have a number of instruments that are playing at the same time, we can hear the distinction between the different instruments and the different notes that they're playing as well. And then we can focus, we can say, I want to listen to a particular instrument. And this is what sound engineers do when they're mixing. So they can listen to the song and they can say, right, I need to focus on the bass guitar, for example. And you can literally focus on that, even though the other sounds are going on. And you can treat that sound according to the treatment you want to give it. So
and it seems you also train this ability to identify different sounds. Because in my own experience, I remember when I was trying to play the guitar many years ago, when I began playing the guitar, it was very difficult for me to distinguish notes in a chord or to distinguish different musical instruments. I just heard the whole song or only maybe the voice line. And as you get accustomed, then you get better at dividing and stop seeing everything merged, but actually seeing different lines and see where things are. And what you're saying about colors, how they merge, how it's impossible for the eye, for the retina to unblend, to separate, for example, the blue from the green once they are already blend. Yes, that is true. But it also makes me think about, well, how wide is our ratio, how much we can perceive with our eyes, how much we can focus on. And in terms of waves, what's the limit? Does it depend on every person? Some people can hear 12 simultaneous instruments and knowing what's going on, which note is each of these instruments doing, and other people might have trouble doing this, or how is it?
I think it depends. One good point that you mentioned was that when you first started with music, I had this myself. You would listen to a song and you could hear everything as one thing, and you couldn't really distinguish the separate instruments. But the more that you listen and the more that you train yourself, it starts coming really automatically that you start to be able to distinguish quite easily between the different instruments. So it really is a matter of training our ears to hear. So because I think our hearing is so spontaneous, and in fact, there's a phrase in sound research where you say you can't close your ears. You can close your eyes. You've got your eyelids, so you can close them. But you can never close your ears. So even when you're asleep, you're still hearing, even though unconsciously, you're switched off to the conscious realm. But your ears are still receiving information. And this is, I think, where, because it's happening all the time to us, we're not really trained to use it as a sense to listen carefully for details. But it's not because we don't know how, because unconsciously we've been trained to do that through, very natural things. But it's only when you start becoming aware that you can actually distinguish between different sounds and you can hear them, that you start to be able to determine them more quickly, and to be able to distinguish certain things. Don't forget, in sound, you still get a phenomena of masking, where if you have sounds which are in the same frequency realm, they do cover each other. But then if you have spatial separation between those two sounds, you can still hear them distinctly. If you don't have spatial separation, then the signal can get mixed up. So this is where it's similar to color. This is
of course, they're masked one behind the other.
That's it, yes.
Sound is masked by the other. And I guess these little details are very important when it comes to sonification in astronomy, in earthquake activity.
Very much, very much. This is where I think the sonification, so going back to sonification and the whole idea of using sound and listening as an aspect of data analysis, is that you're designing a system for the people that you're working for. That's very important. So I put up a slide here. There's a list of examples of all the different uses of sonification. And we can see it in astronomy. Very simple one that I think a lot of people are familiar with is a heart rate monitoring machine. So we can immediately hear a change in the speed of the heart rate. So again, this is the tempo related aspects of sound that come in. And that's very important for doctors, because if your heart rate is suddenly racing when it should be working at a slower rate, they can immediately come and monitor you. It could be used for monitoring cell behavior or molecules. So these things can be sonified and we can hear how they behave. The most classic example in sonification is the Geiger counter, which is for measuring radiation. A very simple device that increases in frequency, it increases in amplitude or volume or loudness, whatever you want to call it. And that way we can tell whether there's radiation in a particular area or whether it's safe to go into that area. It's used for earthquake activity, as you mentioned, oil drilling. So there are a lot of applications for it, but then one has to understand how the data can be translated into sound. Okay, so there are different techniques of how to use sonification. Now in astronomy, there are two main examples of sonification that are used. So these are the two main ones. One of them is called audification, and the other is called parameter mapping sonification. So if we look at audification is when you directly translate the data waveform into sound. So if we go back to the example of earthquakes, normally if you get a reading of an earthquake and you get a graph which is visually showing you how an earthquake is actually working in terms of the Richter scale, then you can actually put that graph into a computer and translate that into sound. You would probably have to shift the pitch of the frequency to bring it within the human audible range. But once you're able to do that, then you can hear how the earthquake is actually working. So that's the most simple form of sonification. It's used in astronomy a lot. So examples would be, it's been used a lot with solar radiation or solar wind. where they actually get the representation, they translate that into sound, and they can hear how that solar wind is working, the frequency of it, the extent of it, size, and all this. It's used as well. For example, there was a classic audification of the rings of Saturn, where a microphone was put onto a satellite, and as it passed through the rings of Saturn, the Cassini spacecraft, it could pick up all the different asteroids that go around the planet, and that information was audified, and they could hear it. And it sounded like a machine gun, which was an interesting comparison. But yeah,
I think you're introducing a very interesting concept, because you actually have to manipulate sound, or you have to take decisions in order to make it audible. You were saying that you can take that graph, and well, you have to be sure that if you put that graph into sound, that has to be audible, that has to be within the human range, audible frequency. And also, well, if you have numerical data and you want to present it as sound, well, you said the most simple thing is just to take the graph, which is already a representation of data, and then translate it into sound. So it seems to me that, at least in that example, you are beginning, or at least you are departing from a graph or a visual information, and then you are translating it into sound. But then when you gave the second example of Saturn, in my mind, I was thinking, well, isn't this just recording? Weren't they recording the sound, the actual sound? So what's actually going on? Are they actually recording waves? And well, from what I understand, if there is no air in the space, in the outer space, then you cannot really hear the sounds. So are they actually recording waves, which then are translated into audible sounds, or how does it work?
It's a bit of both. So in space, it's not a complete vacuum. What you have gas pockets, and these gas pockets allow sound waves to travel within them. The only problem is that most of these gas pockets, they're quite sparse in the amount of gas that you find. And so what happens is that the sound wave is very slow, and it needs to be speeded up so that it comes within the human hearing range. So to speed it up, you have to pitch up the frequency, basically. And yeah, this is where, for example, there's an example of the gravitational waves that were captured recently by LIGO, and that was sonified using audification. Those waves they've arrived and reached the Earth at such a slow speed that you wouldn't be able to hear them if you just grab that wave and you convert it into sound. So you have to resample it a number of times to bring it within the human hearing range. And then you could hear the actual gravitational wave taking place. And it was like a rise in frequency, which was like that. And that showed two black holes that were merging into each other and causing a ripple effect of gravity that came, we were able to detect on the Earth using very refined instruments. So again, even with earthquakes, the earthquakes themselves, we're not always hearing them. So if you've got an earthquake on a lower scale, earthquakes are happening all the time. If they're lower than, let's say, 5.6 or 4 on the Richter scale, we won't really hear that. We could feel it, but not really hear it. So in that case, the wave's massive. You can imagine a wave which is kilometers long. Now, if you put that onto paper, you'll need paper which is like kilometers long to be able to represent that. Whereas with sound, you just resample it, speed up or pitch it up, so to speak. And once you raise the pitch, you can hear that earthquake. And then you can tell, how strong it was, and where it happened as well, and the distance and everything. So this is where audification comes in very handy.
Yeah, it comes with a lot of detail, because this is much more interesting that your everyday Hollywood setting, where space is a vacuum, you don't hear, that's it. But here you're talking about different concepts, like pockets of gas, where sound can travel, but maybe it travels so slowly that you can't really hear it. So you have to manipulate it speed it up so we can hear it. And when you were given the example of the wave in an earthquake, of course, if you would like to be, if you would like to work in a scale 1 by 1, then you would need a sheet of paper as long as the earth itself, or as long as, I don't know, as the continent, or the wherever the area is where the earthquake is going on. So you really have to translate, change the size, resize, make it bigger, longer, so it is actually audible or visible.
That's it. There was a classic example when pulsars were discovered. They recorded the pulses, which were radio waves. So it's not just sound waves that are picked up in space, you've got radio waves as well. So we collect those using radio telescopes. So we're actually collecting a wave, we're picking up that information, which is the same as recording a sound wave. It's just it's a different type of wave on the electromagnetic spectrum, but it's still a wave. So basically it's the same thing. It's just happening at a much faster rate. And at first they didn't know what pulsars were, and they called the signal little green men. So this is where they thought that they actually discovered life in outer space, or extraterrestrial life. When they looked at the data, first of all, when they printed out the paper, it was so long, I think it was 5 or 6 kilometers long, if I remember correctly. And they just couldn't go through it. It was just too much to go through. So they audified the data. And they used a very primitive means of picking up vibration, where I think they had I think if I remember correctly, it was a metallic device that would resonate. And from that resonance, they could pick up the pulses that were happening. So the pulses are like tick, 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 and they're very constant. So in that case, if you audify that, you can immediately hear that there are pulses going on. And you might, from that, they were able to tell. So this is how refined the human hearing capability is that they could tell that it wasn't like a radio signal that we send out into space. It wasn't a civilization trying to contact another civilization. They realized that it must be some kind of star which is moving on its own axis and creating a pulse of radio waves. When later on they could observe that phenomena, they confirmed it. And yeah, but the audification helped them to realize that the star was actually pulsating at a very fast speed. And because of that, it was ejecting radio waves.
And it's the same information. We have the same information put into paper, which is difficult to understand and analyze. The paper is too long. You have to look at too many things. And that this information translated into sound, it becomes more intuitively understandable. And you realize, oh, there is a repetitive pattern. There is a pick, or there is a bit here. Mm-hmm. And also, we get over the misunderstanding about another civilization trying to contact us. They realize, well, this might be a star, or this might be a spinning star, or a couple of stars.
That's it. So, it's amazing. I mean, there's another example when you look at the surface of a star. The surface of a star, going back to the gases that you find in a star itself. What happens is the sound waves actually start bouncing off the surface of the star. And that affects it affects the actual star's circumference. So from this activity of sound waves, it's called astroseismology, and astronomers can actually measure, the size of the star's surface and how it's fluctuating according to the sound waves that are bouncing on the surface of the star. So again, that would be audification. They audify that data, and they can hear. Because the thing is, if you get one star and you get another, and you hear the sound waves of one and you hear the sound waves of another, and the way that they're pulsating, you can start hearing patterns or differences. And you can say, right, okay, so this star is probably smaller than that one because the waves are going at a faster rate. Whereas a bigger one, the waves are going to be longer because they've got a longer distance to travel across the surface. So it's these very small details that can tell a lot about the nature of the star.
And these details are easier to understand when it comes to sound than seeing a graph. Well, I have a question. I see here audification and parameter mapping sonification. We have two concepts here. And what's the difference between the two, audification and sonification?
Okay, so let's move on to parameter mapping sonification now. So in the case of parameter mapping sonification, you're not directly translating the wave, in terms of pitching it up and down and resampling it. What you're doing is you're using the attributes of hearing. So earlier on, when we gave the example of the siren, we mentioned loudness, we mentioned the clarity, or something called timbre. Okay, we mentioned pitch, which is the frequency, how fast the wave is actually moving, which we hear as differences in musical notes, basically. You've got the rhythm, which is how frequent the frequency is beating, and spatial dimension, where the sound is actually coming from. So we're using these attributes of hearing, and we're mapping those attributes to the data. So it's a bit more complex in this case. You're not just putting the graph in a computer program that will translate the sound. In this case, you have to map out each of these, they're called psychoacoustic attributes, to the data. So this is a more of a, it's more of a
I'm sorry, could we go once more through the acoustic attributes? Which are the four? I think you mentioned four of them, right?
Yep. So we've got loudness, which in scientific terms is called amplitude. We have timbre, which we can call it clarity, just to simplify it. Timbre is a bit more complicated than that, but let's call it clarity for now, which is an aspect of timbre. There's pitch, which is the frequency. So as we mentioned, if something moves faster, it sounds higher in pitch. If something moves slower, it sounds lower in pitch. So it's a lower note. I've got a couple of slides which will be coming up later, and we can look at these in more detail. And then you've got the rhythm, so the rate at which the thing is beating, the frequency is beating. And you've got the spatial dimensions, which direction the sound is coming from. So again, with the siren, if you're crossing the road, you hear it coming from the right-hand side. The loudness is low, the timbre, the clarity is not clear, and the pitch it's there, but as it starts to move towards you, you start hearing the pitch changing. Now, why does that happen? It's because the waves, the distance between you and the ambulance is becoming shorter. So the wave, the frequency of the wave is becoming faster. So that causes a rise in pitch. And as it gets closer, you hear that there's an increase in loudness, an increase in the clarity. It reaches you, suddenly it moves away, the loudness gets quieter, the clarity or timbre starts to reduce, it becomes less clear, and the pitch starts to go down because the ambulance is moving away from you and the wave is becoming longer again. And you can tell the direction, so you're hearing it going from right to left, and you can hear that very clearly as well.
Now that you mention it that way, when you reduce the space, when it's shorter, it's faster, right? Because actually the wave itself, it's going to be shrinked, right? It's going to be smaller, so it's going to be faster, and somehow that exemplifies how shorter distance is shorter time. Also, if I want to get to a place which is closer by in terms of space, I also get there faster. And it's beautiful how waves themselves, they also shrink, and then you hear them higher. It's
yeah.
Very nice metaphor.
Yeah. And it's interesting because if you measure frequency, you measure it over amplitude, loudness over time. So the loudness is the energy of the wave, the sound wave, and the time is how much time it takes for it to actually manifest and to reach our ears or to leave the source that it's leaving from. So this is it with the parameter mapping. It's more of a designed form of sonification. This is really where sound design comes in. Now, one thing I want to make clear is that with parameter mapping, there's no specific technique how you map these parameters. Okay, so you can map them in any way you want to. There's just a few rules that apply where, for example, if you use amplitude or loudness as your main mapping, it's not very effective. Because sometimes if two things are of a very similar loudness, you don't really hear the difference. But if things are of a similar pitch, but there's a slight difference, you'll hear that difference in pitch. So classic example, and let's relate this to timbre as well, or clarity. When you're speaking to people, you can distinguish a person's voice immediately if you're familiar with their voice. So on the telephone, that's very important because you can't see the person. So what we're hearing there is the way the tonality of that voice, which is the pitch and the timbre, are manifesting according to the person's voice box and the shape of their mouths and how they talk and everything. But this is what allows you to tell the difference between your boss at work or your colleagues if they're calling on the same line, and whether they're male or female. So males have got lower voices, lower frequencies, and their pitch is lower. Usually, you do get women who have low pitch voices, and you do get men who have high pitch voices. So, but the general rule is that you get these differences in pitch, and then everyone has their distinct characteristic because of the shape of their physiognomy, their noses, their lungs, their voice boxes, their mouths, and everything, their tongue, teeth, the whole lot. So these are, you see, when you see how refined all this is and how you can tell so much detail from very simple things, when you put these mappings together to represent data, it can be extremely powerful. So when you're using pitch or loudness and timbre, the rhythm and spatial dimensions together, then you can have a very powerful data representation.
Wow, thank you. There's so many details. It's so interesting. I see that now you have changed to a new slide where we see gravitational waves and notification of solar winds.
Yeah, so these are the examples. We mentioned some of them in relation to audification. So we mentioned the gravitational waves and audification, the astroseismology. You've got Earth radiation activity, which can be audified. There was atmospheric work in Jupiter, where a lot of this was audified as well to be able to hear certain aspects like aurora borealis, which happens in Jupiter's planetary magnetosphere. We mentioned Saturn's rings, and yes, magnetospheres as well, heliocentric activity, and we've got the audification of Jupiter's auroras, which I just mentioned. With parameter mapping, then we go into stuff like X-rays, solar data again. Solar winds can still be sonified using parameter mapping. Star maps. So when you have a collection of stars, you can sonify that data, and you could hear the differences between different stars and their ages. So that was one example that was seen in astronomy. Planetary orbits is very interesting. So you can actually build a model of the solar system using parameter mapping sonification, and you can actually rely on the sonified data without having a visual reference to be able to tell the differences between planets.
Wow. So you actually hear the model, but it's difficult to imagine how you can hear a trajectory, how you can hear the size of a planet, the amount of energy it's projecting, etc.
Again, it really depends on the mapping. So if let's take, I mean, one of the first sonifications I built was the model of the solar system. So in order to represent differences in the size of planets, I used pitch. Okay, so as we said earlier, if you've got a larger object, then the sound waves are actually going to travel at a slower rate across the surface of a star, let's say. Let's take that example as a planet, for example, as well. So I used lower pitches for the bigger planets, higher pitches for the higher planets, and I used it on a surround sound system. So in that case, what you can hear, the rotations of the planets as they go around your head, the differences in speed will determine the orbits of those planets. And this is where you can hear Mercury going at a very fast rate around the sun, and Jupiter going at a much slower rate, and you can tell that one planet is closer to the sun than the other.
So this low volume represents objects with higher mass, and they'll be spinning slowly in your surround system.
It'll be a lower pitch in this case.
A lower pitch and a slow velocity going from left to right as well?
That's right, yes, yes. So let's say I used a sound system which consisted of 4 speakers. So you could hear the rotation of the planets literally going from the front to the back and around again. And you could immediately tell the differences in speeds between different planets.
There is an example you showed me before, and well, we haven't really talked about this, and it's the asteroid collision. I was listening to this sound sample, the asteroid collision, and I can hear it going left to right. Do you think I could play it now so other people can hear it? And maybe you could try to interpret a little bit what these noises are.
Okay, sure.
Okay, thank you so much. So what I'm going to do now is I'm going to play a sound from my computer. So I want to be sure that this is going to work and everybody's going to listen. So I will change also to the Spanish channel. I'll say the same thing. Sí, en este momento nos gustaría, entonces, me gustaría a mí poner un ejemplo de sonificación. Entonces quisiera saber que en términos técnicos, si es posible que yo le dé ahorita play y que se escuche.
Señor.
Okay, so I'm going to do this. I'm just going to play it and see if Michael can tell us a little bit what's going on here, because all I can hear is noise. It's a very interesting noise, though. So just one second. I don't know if when I hear something like clapping or hitting, does that represent a collision?
Yep. Yeah, it does. Now there's a difference between the different hits. When you hear the higher pitch hits, those are smaller asteroids. The lower pitch hits are bigger asteroids. Now, that particular sonification was designed because we were trying to detect a planet within the asteroid belt of that particular exosolar system. That system is the Beta Pictoris system, which is a couple of light years away from the Earth. When you look at the Beta Pictoris system on a telescope, you see this huge asteroid belt surrounding the star. And this is because it's still a developing solar system. It's not as developed as our solar system. So when solar systems are developing, what happens is that, first of all, you get like a huge dust cloud, and you have a star forming in the middle because of gravitational influence, which is heated up energy, and the star starts to rotate on its own axis. And as it does this, a ring of gas and dust starts to rotate around the star. Now, it's believed that the rotation of this disk is called an accretion disk, moves at the same speed as the rotation of the star. Now, as this system cools down over time, these dust clouds start to form into rocks. They start to form into asteroids. And slowly, they start to form into planets. Now, with the telescope, it's very hard to see the planet in the asteroid belt. Okay, so the whole idea of the sonification was, let's listen to the asteroids colliding. Now, how could we tell there were asteroids colliding? When you look at the actual disk of the asteroid belt in the Beta Pictoris system, it's a wave. It's not flat like that. It's more like that. So you got the top and the bottom. It's a wave, okay? It's more like an S shape like that, which means that there's some kind of influence which is pushing asteroids outwards, and creating a ripple, a wave, so to speak, in the belt, okay? So they were able to mathematically calculate the asteroids and their collisions due to observations over time, constantly looking at this belt and seeing changes as it rotated, okay? So what happens is every time an asteroid goes in front of the star, it blocks out the light. And depending on the size, if you've got a small object, it will block out a bit of light. If you've got a big object, it will block out a lot of the light. Okay, so they started creating a model out of this. And then from there, they wanted to see what was disrupting the system to the extent where you were getting this ripple effect in the wave. They suspected that there was a planet. The sonification, when we heard it, you could hear that every now and then you could hear these low frequencies coming in. Like that. That means that the planet is passing through, and it's hitting the bigger asteroids. Now, the big asteroids could be as big as the whole of South America, for example. Okay, they're massive, they're huge. They're not small rocks as we know them on the Earth. They're huge bodies in space. So there must be a much bigger body which is knocking them. So as the planet passes through the belt, what it does, the asteroids start getting knocked about and they start colliding with each other. Now you hear them going left and right because the planet is passing through, so it's moving asteroids out, which are hitting the asteroids on the left and right to the planet for its trajectory. And the astronomer could immediately tell that there was a planet passing through that belt just by listening to that data. So that's how effective the sonification can be for these kind of things. But it's very important to state here, the mapping we had decided beforehand, and she had said to me that she wanted the bigger asteroids to sound larger, okay? So in that case, we decided to use lower pitches, and the higher ones to sound, the smaller asteroids to sound higher pitch. If you throw a small stone, it makes a very high pitched sound. It goes when it falls. If you throw a bigger stone, it goes it's lower. Another example could be if you bounce a basketball, it goes thud, thud. If you bounce a tennis ball, it goes. You see the difference in pitch? And we can tell that immediately. You can tell if someone's bouncing a basketball compared to a tennis ball. And it's the same with these asteroids. As soon as you're hearing the lower pitch the lower pitch asteroids, then you can tell that there's a bigger body passing through. So we weren't listening to the planet itself passing. What we were listening to was the path it was creating as it moved through the system. Now, that sonification was designed to work on a surround sound system. So you could hear it moving around your head as it passed through.
For me, it was very clear as I hear it going from left to right and vice versa. And it is amazing now that you explained it, how we're actually listening to a younger solar system than ours. And we see all this, well, we hear the planet going on its orbit, crashing with the asteroids, and how they are being just pushed away from side to side, and you can hear that. It's absolutely beautiful, you know. And when you make the sound, you're like this beatbox of astronomy. This is very interesting because it's such a mix of rhythm of something which is vernacular, or something which really belongs to our spirit, and a knowledge of something which is well, you said this this precise solar system was around 2 light years away from our solar system.
I think yes. I think it was about, let's say, four or six.
Okay.
I can't remember exactly, but yeah, it's quite close to us in terms of proximity. But again, close, but it's still difficult for us to see this using telescopes. You see, we're always
Yes,
seeing
because all we will see is these clouds of rocks, and we wouldn't distinguish a planet from an asteroid. It would be difficult to see the whole picture clearly.
It's very hard to see because all we're seeing is dips in the light on the star. So we're not even seeing whether it's planets or clouds. We can't really tell that.
Okay, it's just absence of light and light.
That's it. Yeah, yeah. So a lot of the models, even the visual models, are still mathematical representations. So even when we say that we're spotting planets, there's a lot of study that goes into that to confirm that it is actually a planet. There's a number of observations, or over time, and what they look for is, astronomers look for repeated patterns to be able to confirm that they are actually looking at some kind of planetary body or asteroids or so on and so forth. So this is where these examples that we have listed here, sonification works quite well with that, because what you're doing, you're still looking at waves, and then you're using sound, which is waves, and you're using the characteristics of the wave to actually be able to perceive these these celestial phenomena, so to speak. So I think one of the big advantages is because you mentioned the rhythmical aspect of that sonification that we listened to, and again, that goes back to the aspect of time and the use of time. So astronomy is mainly temporal data, or time-based data, or spectral data. And we could talk a bit about spectral data as well, what I'll do. So before I move on to that, I just want to emphasize once again that when you're designing a system which is a parameter mapping system, it's highly advised, I'm not saying you have to, but it's highly advised to design the system around the astronomer, okay? So in this case, when I designed that sonification that you played, I used a user-ended design approach, or a UI, user interactive, or user interface, or user experience design. So that means that I don't know enough about the data. I'm not an astronomer, okay? I'm a sound designer. So the astronomer has to guide me and tell me what the data is representing. Now, when the astronomer describes the data, they relate to it in certain ways, and they use certain words. So with that particular sonification that we listened to, we're talking about asteroids there, and asteroids are composite of rock and ice. So the astronomer wanted to hear something that sounded like the breaking of ice. So that sonification, if you listen to it carefully, you'll hear it sounding like when ice is melting, when you've got a river or a lake that's frozen over in wintertime in colder countries like Canada or Russia, or when the temperature starts to heat up, that ice starts to make very like rhythmical sounds, which are very fine, like cracking sounds. So we designed it to sound like that simply because the astronomer made that immediate association. She said, I imagine asteroids as being colliding bits of ice and rock. So my whole idea was to design it based on that description. So it's very important then, you're never going to get it completely right with your first design. You've got to, it's prototyping. That's called an iterative design process. You send it back to the astronomer. Does this make any sense? Does this sound like your data? Don't forget, most astronomers have not used sonification, so they can't even imagine how it will sound, you see.
Which is actually good, because you have to work hard in order to make it audible and clear to someone who is not used to listening to data.
That's it, yeah. And like we mentioned earlier, we're not really trained to understand our listening process. So This is where the iterative design process really helps even the astronomer to learn about that. So, you know, once you start explaining, okay, we're representing the data here by, we're using pitch for the different asteroids. And as you know, the smaller ones are less clear, but the bigger ones, we made them sound clearer when they collide, because that's what you're interested in hearing, and they're louder, you see. So these are the small things, going back to the psychoacoustic properties used to map the data. What you're doing is, she mentioned to me, right, I am interested in the bigger asteroids. I want them to sound clearer. I want to be able to distinguish them from the smaller asteroids easily. So these are all pointers from her description. I could tell, right, okay, so we need loudness, we need a difference in clarity, we need a difference in pitch. So she was telling me how she wanted it designed, basically. And then because I understand the psychoacoustics and how to map them, that's where the sound designer comes in. And he could say, right, according to what you've told me, I've designed it accordingly. Now, does this agree with what you had in mind or not? And they can say, right, could you give me a bit more clarity on those lower frequencies? Or could you make the pitch not so low because I can't hear the differences? So one important thing to mention with parameter mapping is that it's very important to create scales within which these psychoacoustic characteristics are going to change. Okay. Now, we mentioned the human frequency range. We can hear things happening from 20 times a second to 20,000 times per second. That's the frequency rate within which we can hear. Okay. Now, at my age, I'm in my mid-40s, so I can't hear up to 20,000 hertz anymore. I can't hear 20,000 times per second anymore, because your ears start to lose that ability. Now, it was important to know the age of the astronomer, so that when you set the range of the pitch, you don't set it within a range that the astronomer can't hear. Now, this particular astronomer was still in her early 30s, so her hearing range was more broad. Other astronomers I worked with were in their 40s, about a year older than me, so I had to make sure that the range that I chose was still audible for them, that they could hear that range properly. Now, within the range of the frequency changing, or the pitch, you have to make sure that it's not too loud that you're blasting their ears. So the loudness, you have to regulate how loud, from how quiet to how loud it will go. If it's too quiet, they might not be hearing it, especially if you have more than one signal that you're listening to. And the clarity as well, you have to make sure that you're not using specific frequencies which are so clear that they hurt the ears. You want to make it as comfortable as possible for people to use.
Audible, but comfortable.
Yeah, because what you get, sonification has been shot down a number of times because people have produced sonifications without taking the user into consideration. And then to the user, it just sounds like noise because they're not understanding how it relates to the data. So this is why this approach here, the user-ended design approach, is very important, because you're designing for astronomers. Astronomers
You have to make sense to the other, of course.
That's it. Yeah, exactly. So,
and it is making me think about how many possibilities are here. For example, for people who are visual impairment, they could really profit from this, because you can hear the information which you usually cannot see with a level of detail which I wasn't aware of, like how much information you can actually transmit just through frequencies, through volume, through a change in pitch. It's absolutely amazing. And I do have a question. What happens, because I come from human sciences, so that is my concern now. Do you think it's possible to show data, let's say, for example, if we want to show how much water is left in a forest, or we want to show how deforestation is growing in a certain area, or how the conflict, war and armed conflict, it's affecting a population. And we have the data, we know how this is working, we have the map in the territory, we see how people are moving, how water is receding, etc. Do you think it's possible to create a sonification which shows this and which is also intuitive, where you can actually hear the water, hear the people, the machines, and use all these parameters in order to show which regions of let's say, Colombia are more affected than others?
You could. That's a very good question, actually, because what you're speaking about a lot of spatial data here. So you could map the sonification to work in a way where you're seeing it, you're hearing the sound extending from a central position out to your left and right ears to be able to get an idea of which way, let's say, conflict is happening on a particular map, or forestation or deforestation, how much it's reducing. In the case of water, the flow of water, you could use pitches. When you have more water, you have lower pitches, more loudness. As it reduces, it gets higher in pitch and probably less loud. So there's so many parameters you can play around with in order to use sonification to represent this data. So what you might have is, you might have a visualization of this, which is, for now, we mostly use two-dimensional representations, even though there is virtual reality, which helps us to extend into three dimensions. But to graphically create three-dimensional representations takes a lot of time. Sonification is probably easier to build. So you could actually have a sonic representation of what you're seeing in the map. And you can see over time how the forestation, if you've got, let's say, a green zone, which is that big, which is darker green, and over time the deforestation is shown as a lighter green. You can hear that difference, and you can hear that over time. So the time factor here is very important. If you've been collecting that data for the past 5 years, you can reduce those 5 years into 4 seconds, because you can control the playback speed, you see. So in that case, what you can do is you can get a really good impression in a very fast amount of time. And you can compare this to other regions in Colombia where there has been a similar thing going on, let's say deforestation. And you can say, right, this one happened at a faster rate than this one over the past 5 years. Because you'll hear it. You'll hear one going fast and the other going slower.
Exactly, and I think it would be in the case of the Amazon forest, which is in great danger right now. It would be also a way to actually listen in how fast in the last 5 years things have been going on. Like, because if you take the last 100 years, then the process of the deforestation it's important, but it's not as fast as it is happening now. So when you hear that, I think it would be very I don't know, like very emotional also in one sense, like something that actually touches you directly, more than a report or direct information.
That's it, yeah. I mean, if we go back to that example of sonification that you played of the planet moving through the asteroid belt, that data set is massive. What you heard there, we only went for a sample of 30,000 days there of that planet moving through the belt. The data set itself was about 5 million days, I think, because it was a mathematical model. So they haven't been observing it for 5 million days. That's way beyond our capability. You know, we don't have time machines to do that. But yeah, what they did is that from the pattern that they could observe, they started to calculate how that pattern would change over time using, you know, machine learning algorithms and so on and so forth. And the data set was 5 million days. Now, we heard 30,000 days, which is still a lot. We're talking about quite a few years there. And we heard that in 2 minutes. And we could even hear that at a faster rate if we wanted to. So you see how you can compress the data, that the whole idea of time is so intimate when it comes to sonification.
And you're compressing the data and still you're getting the fundamental information. It's like abstracting directly, you're directly abstracting. Yeah, this is very interesting because it's something that usually human minds do, that we do, but this is something that sound itself does.
That's it, yeah. So yes, I can see that sonification, with a good design, it can be applied to many different things. I mean, let's look at it this way. I've been using it in astronomy astronomy is spatial mapping. So if you put that on the Earth and you're looking at geographical features and social features over space and time, then it's exactly the same thing. It's exactly the same as observing that in outer space. Because in outer space, you have a position and movement over time of the planet, let's say, going around the belt. So that you've got a map there. It's a two-dimensional map. So that's where it's really interesting. So what I'm going to do now, I'm going to speak about one specific sonification that I did design, which was the whole idea. I worked with an astronomer from NASA on this. What he studies is the atmospheres of exoplanets, which are situated in the habitable zones of exosolar systems. So the Earth in our solar system is in something called the habitable zone. It means that the conditions are just right. We're far enough from the sun to allow us to have water without it evaporating. The heat on the planet allows us to survive without us being fried to a cinder or frozen to an ice block. And they look for similar conditions like this when they observe exosolar systems to see whether it's possible that there is extraterrestrial life which is similar to ours in other solar systems. So one of the things they do is they study the atmospheres of these solar systems. And to do that, they use a technique called spectroscopy. So spectroscopy is the study of the electromagnetic spectrum of light. Now, the electromagnetic spectrum of light is split across, you know, if you look at the colors of the rainbow, that's where you have the electromagnetic spectrum of light. White light, when it goes through a prism or some kind of reflective surface, it disperses into 7 different rays of light, which is it's basically what we can see. That's how far that, you know, we're in hearing, we can hear from 20 hertz to 20,000 kilohertz, like we said, and with vision, you can see between the 7 colors of the spectrum. So if we take a look at how that data is actually collected, you can see the diagram here. You've got the star, and as the planet passes through in front of the star, so these observations are done in transit, okay? And a snapshot is taken as the planet comes right in front of the star, because what happens is the light passing through the gases of the atmosphere are absorbed. And according to the level of absorption of the particular gas in that particular atmosphere, we are able to tell whether an atmosphere contains oxygen, hydrogen, helium, carbon dioxide, methane, nitrogen, and all the qualities that we find in our atmosphere. So by observing
just to make it clear, when we talk about light absorption, the phenomena that we actually experience, it's a color, right?
That's it, exactly, yes. That's a good point, yes. So each one of these spectrums that we're mentioning, hydrogen, oxygen, methane, they all have a different wavelength. The wavelength is color, basically. It's a wavelength of color. So in the example, we're seeing methane here, which is being absorbed. And methane in our visual spectrum is represented as the color green. So in the green,
I think you have to move forward the slide because we are not seeing the gases. You said you talk about methane.
If we go to
there you go.
on this particular slide, actually, you see there it says methane in the planet's atmosphere absorbs starlight.
The green wave. That's
yes. Yeah, that's the color of methane. And as you mentioned, if we move on, this is what hydrogen, helium, oxygen, carbon, and iron will look like in the atmosphere of a planet. As you can tell, we have the black spots. That's light that is not coming through. Okay, it's not being absorbed. It's going right through the atmosphere. So in that case, we can see that the quality of iron is less absorbing than hydrogen. Hydrogen is a lot more absorbing. And all the different colors that you have there, we have that, you have those lines coming up. Those are the hydrogen aspects in that specific spectrum. And you've got the same in the helium. You have those very fine lines in between. Those are the photons. Photons are light particles which are emitted by that particular chemical. Okay. Now, in this specific study, what we were looking at water vapor in the planet's atmosphere. I wasn't told which planet we were observing, so this was all top secret information, but anyway. But here's actually what you're looking at here in this slide. You've got the graph of the signal that we were analyzing, okay? The graph, you've got two aspects here. You've got something called the wavelength, which is what we spoke about, which is the wavelength of light that is observable by the human eye, okay? Which is measured in microns. So this is the amount of light in that color spectrum that we're able to see. And there's something here called the effective transiting radius, which, as you can see, it's in kilometers. Now, what this is the amount of light which is bouncing off the planet's surface and creating a kind of corona around the planet's the planet's surface. So if you look at the planet, it looks like this. Imagine that's the planet, and this is the light bouncing off the atmosphere. Okay, and as you can see, you've got different ranges of kilometers there. Now that's because some of the light goes all the way down to the planet's surface, so less of it is reflected back out, and some of it bounces off the clouds. So here we can tell whether there's clouds every time you get a peak, you see, because there's a lot of absorption going on because the clouds contain these different chemicals. So a rain cloud contains a lot of water vapor, and in this case, it's going to absorb a lot more of the light signal than than the other chemicals that we're looking at within this wavelength. So these are the two things that the astronomer wanted to measure. Now, just to make this clear, we've been stressing throughout this presentation that sonification is good for temporal data. But in this case, we're not looking at a temporal data set. This is a spectroscopic data set, not a temporal one. Okay, so how are we going to use sonification effectively if it's not representing time?
Yeah, because when it comes to time, music and time, they go together. It seems intuitively correct. But when you're representing only a wavelength database, that's much more difficult.
Yes and no. Well, if you notice, if you look at the graph, which is moving between 0 to 20 microns at the bottom, you've got an actual wave pattern there, you see. So that even though it's not really happening over time, that is one instance in time, but the fact that you have a frequency is time. You see, so we're measuring this wave over, we're still measuring it over time. So what we decided, apart from the signal that you get, when they collect this data, what happens is the telescope picks up a lot of noise with the signal. The signal's never clear. That graph that you saw is the filtering of noise, okay, from the collected light that they captured from that specific planet. What happens is they try to filter out the noise using a number of mathematical formulae, okay, to do this, using low pass filtering, band pass filtering, high pass filtering, so on and so forth, to get rid of the noise. But then they need to compensate for areas where the noise has corrupted the signal. So when they actually produce the signal's not as, I'll go back to the graph, it's not as clearly represented as you see it there. So they have to mathematically calculate how much data is lost because of the noise. So one thing the astronomer wanted to do, he wanted to measure the signal in comparison to the noise. Now, unfortunately, I don't have a graph which shows the signal and noise at the same time, but I can show you with my hands. If you've got the signal and you've got the noise on top, what happens is that the noise, let's say, right, let's make the signal a bit more complex and the noise a bit more complex. So you can see the signal underneath the noise, but what you're not seeing is where my fingers are in the way, you could be losing amounts of data there, okay? So the astronomer wanted to see if sonification could help him to identify water vapor features that have been lost or masked by the noise. So one thing in the design was, the first thing that was obvious was actually being able to separate the signal from the noise on the left and right speaker. So if you're hearing that, you're hearing them as two separate things, signal and noise on left and right speaker, okay? That was the most obvious thing that we were looking for. So we described the idea, we're not working with temporal data here, but we said that we could change the wavelength data into time. Now, one of the flexibilities of changing that into time would be that we could affect the playback speed. So, you know, we mentioned earlier that you could listen to the sonification of 30,000 days over 2 minutes. You can play around with that speed. It doesn't have to be 2 minutes. It can be, let's say, 50 seconds. It could be 4 minutes, depending on how much detail you want to hear from the sonification. So it's literally like you're grabbing that graph that we saw earlier and you're stretching it, you're zooming in.
Yeah, it's
rather
precisely the opposite phenomenon, right? You had, you know, thousands of years of information. You had to show them in 4 minutes. Now you have less than a second. You have like very, very small information and you have to zoom out so you can hear it.
That's it. So in this case, we had 19,800 lines approximately of data, which are all part of the wavelength. And as you can see, we could map the wavelength to the playback speed, the selection. So you didn't necessarily have to listen to the sonification from the beginning to the end. You could choose segments and listen to those particular segments. And you could loop the playback. Now, looping means that you repeat the playback. So you could choose a specific segment, or you could listen to the whole thing over and over again. Okay, so this is the manipulation of time, basically. Now, I don't know if you've got the presentation open, David, at the moment. I've got a couple of audio examples there. I was wondering if you could play back at least one of each or something like that.
Sure, I will do so. So here I got it. Okay, let's listen. I'm going to play back at 3 milliseconds.
Okay.
Okay, should I go to 5 milliseconds?
Go to 5, yeah, and you can hear the difference in the length between them. So as you could tell immediately there, the length of the 5 millisecond one was a lot longer than the 3 millisecond one. So you see how we're manipulating time there. The selection, if you play the selection, what I've done, I've chosen a very specific part of the data set there.
So I'll play the third one, playback, yes, the third one.
That's it. So that is a particular peak. The reason I chose that specific segment was because that was the specific peak that the astronomer noticed that he hadn't noticed before.
Okay, let's play it once more. So what we're talking about is like, woo!
Exactly, yes.
This peak, this going up and down, that's what he heard. And, and that's what he couldn't see in the graph.
Exactly, yes. That was masked by noise in the graph and he was unable to see that. And then if you loop the playbacks, you can repeat that playback over and over again. And it's the same segment being repeated, which is what he did to confirm that he was listening to water vapor at that specific moment.
Let's go back to this example or the last one?
It's the loop the playback. There's a 1 millisecond playback speed there. So there you're hearing it repeatedly, and you can confirm whether or not that peak is of interest or not.
Yeah, there we're just looping that small pike, which was of interest, of his interest.
That's it, yeah. Now in the graph, we also had, so apart from wavelength, we had the effective transiting radius, which I explained earlier, the kilometers of the light bouncing off the planetary surface. So the mapping that we used for this was more complex. The reason being was that the astronomer, he described the data. He wanted it to sound like running water. Now, to create a more natural sounding sonification, you've got to use more than one psychoacoustic attribute to, to make it sound more organic and more natural. So we're using synthesis here, not samples. We're not actually using water. We're using synthesizers to mimic water, not entirely, because we want the pitch to still be more distinct. We just took an idea of making it sound slightly like water vapor so that he could immediately tell that as being different from the noise, okay? And I'll speak about the noise after this slide. So the psychoacoustic elements that we used here, we used pitch, which we explained earlier, the lower notes or the higher notes, the lower radii, the lower effective transiting radii, the ones that don't bounce off the surface so much, would be of a low pitch. So from those examples that David was playing now, you could hear those are the low pitch effective transiting radii, the small ones. When you heard these peaks, that was suddenly the longer high pitch radii coming in. Okay. Just to explain what pitch is here, I've given some audio examples for those of you who are not understanding the term.
So let's play them, right?
Yeah.
Okay. Yeah, let's play the first one, low intensity. Yes, low intensity, high intensity.
No, that's the noise page. Yeah, if you go back a page, there's a parameter mapping signal effective transiting radius. So they're very similar slides. It's just the slide before, slide 17.
Okay, yes. So we have, in slide 17, we have procedure, low pitch and high pitch. No? Am I in the wrong one?
I didn't hear anything there.
Oh, no, I haven't played.
Oh, right, okay. Yep, so you got that. There you got the basketball example. You hear it FUD. It's got a low FUD, okay? If you play the higher one. You've got the tennis ball, and you can immediately hear that one is a bigger. I chose those examples because they're like planets. You've got a big basketball, low pitch, small tennis ball, high pitch. So that's what pitch is. So for those of you who are probably not understanding the term, the timbre, as we said earlier, we're talking about it in terms of clarity here. Okay, so we decided that the smaller radii would be less clear, and as they got larger, they would become more clear. So the peak, you could hear that, that very, I call it a disco laser sound, kind of thing. Where
oh, let's listen to low timbre and high timbre.
Yeah.
That is low, right?
Yep. So you could tell there that the lower timbre was less clear. The bell was less clear than the higher timbre.
Okay, I think I haven't played the high.
You see the difference?
And it's the same pitch, but one is clearer than the other.
That's it. Yeah. So, I'll give a very simple example. With the microphone here, I don't know if it will work, but if I cover my mouth and I talk, my voice is less clear than if I remove my hand. And that's the difference in timbre, okay? The difference in clarity or the tone of the.
Yeah, we could hear the difference, even though you're using the microphone, it's audible.
It's very distinct, isn't it? You can immediately hear that. And then the loudness, as we said, if it's lower, it's quieter. So the lower effective transiting radii were quieter, and as they got larger, they got louder, because the astronomer wanted to hear the peaks. So it was very important to hear them more, especially because you had the noise signal playing on top of the source signal, the water vapor. So they need to be louder so that they stick out. You want to hear the peaks jumping out at you in the mix, not submerged beneath the noise in this case. And then the spatial mapping, what we did, so earlier we spoke about separating the signal and the noise as being signal on the left ear and noise on the right ear. But one thing we decided at a later stage was to have the signal moving. Okay, there's a reason why we had it moving. We're very good at detecting movement through spatial separation, especially if we join that with changes in timbre and changes in pitch. We measure that We're measuring a distance there. So there, it would help to distinguish between the different radii, the effective transiting radii, and the differences in the lengths of the peaks. You see, the very high peaks, you're going to hear them on the right-hand side. The peaks that are not so high will be happening somewhere around this region of your head, and the even smaller peaks somewhere around this region. You see, so that way the astronomer could even tell the differences between the peaks. So it wasn't just a matter of having peaks being heard above the noise. He wanted to hear the differences between them. And the reason being is that specific segment that we played earlier, which was the water vapor aspect that he didn't notice before, was not one of the larger peaks. It was actually one of the smaller peaks.
Okay. In terms of loudness, in terms of
loudness, spatial position. So that played somewhere around the center of the head, not all the way to the right. In terms of pitch, it didn't go up as high as the others, but its intensity was so sharp compared to the other peaks. The other peaks go up over a length of time. This specific one went blam, like that.
Okay.
And that is the water vapor. Do you remember? I'm just going to shoot back to this slide, okay? You see these lines that we're seeing in hydrogen there. You've got like a very light blue or light green line. You've got a reddish line. Those are those sharp peaks, basically. The rest of the data are the lower peaks that you're hearing, and the sharp peaks is the absorption. That's where it's happening. So this is where that really, that really comes out. The noise is different. Noise isn't going to work with pitch. It works with intensity. So the lower intensity in the noise, it was more to the right ear. It was lower in clarity and lower in loudness. So intensity in this case works totally in conjunction with the timbre and the loudness. Okay, that's part of the intensity. The more noise you have, the more it will shift towards the left ear in this case. So the signal and the noise are crossing each other. So what you're getting with that, you're getting spatial separation. So it's easier to hear anything going on if there's a lot of noise. Okay. I don't think we need to play the examples here. I mean, this is just showing, again, the differences in timbre and so on and so forth. So I can move on to now. I mentioned before that we use synthesis to create the sonification. So in synthesis, you need to generate a signal. To generate a signal, you use something called an oscillator. So what an oscillator does, it creates frequency, it creates oscillation. So oscillation, it comes from the word, for roundness, and a wave is a round thing. It goes up and it goes down and it repeats a cycle. And these are called oscillations. So each of the peaks and troughs of the frequency are called oscillations. Each round, so one cycle is called one oscillation. So in order to do that, then you need a specific kind of...
And this oscillator will transform that wave into a sound wave?
Exactly, yes.
Audible?
Yeah. This is actually the audible part. So this is where you get your pitch from. And this is where you can actually hear that signal. It's through doing that. Now, to do that for the signal, we use two types of waves, because waves, you've got your classic wave, which is the sine wave, which is the rounded off wave, which is the most simple form of frequency. But in nature, when we're hearing things, they're not sine waves. They're more complex forms of waves. Why? Because you have more harmonics involved. Okay.
Oh, so sine waves are just a simplified representation of actual waves.
Yeah, yeah.
They are not as smooth as they seem in the graph.
No,
in reality.
No, that's okay. Yeah. So one wave which is prevalent in nature, which is very rich in harmonics, is the sawtooth wave. So I decided to use a sawtooth wave to be able to replicate the water-like sound, to get those rich harmonics. Yeah. Now we can play the example of the sawtooth, and you can have a listen to it.
So I'm going to play that example now.
And then
I'm sorry, that was the white noise.
That's
I
white
was playing
noise.
white.
Yeah.
I'm going to go to the sawtooth wave now.
Okay. Okay, so that's the tone. You've got a pitch there. You've got a specific frequency. That frequency is around 400 hertz. Okay.
Mm-hmm.
So that means that wave is fluctuating at 400 and so times per second.
And when I was listening to it, I realized the high volume stayed for quite a long time. Then it went down. Is that what we see here in the graph when it goes with the vertical line, and then you see a horizontal line on the bottom?
Yes. Yeah. So
and is that length? Are those lengths the length of what we heard?
I mean, the graph isn't an exact representation, but yes, that was basically what you'll hear. And what you're hearing is it's called the decay time of the wave. So it's the length of how long the wave keeps fluctuating or oscillating. Now, we didn't use the sawtooth alone. We used something called a pulse wave, which if you play that now.
Let's go to pulse wave now.
Now, can you hear the difference there?
Well, I'm going to play the second and third one to see if we can hear the difference. I will play the second one. Once more, the second one. So the decay is quite long, right? It goes, it slowly goes down.
You could tell the harmonic data is different in this case.
So and let's see.
Yeah, the sawtooth is slightly different in its harmonic characteristics compared to the pulse wave.
Let's hear the third one, which is the pulse wave, right?
The third one is the sawtooth combined with the pulse wave.
Oh, okay. And now pulse wave only.
So
it's the sharp.
Yes, exactly. So what you're hearing there is you've got when you hear the sawtooth wave on its own, it's got a particular characteristic. The pulse wave has got a particular characteristic. When you combine the two, I mean, my ear is trained to hear them still up to point separated, even though they're playing at the same time. But what you have there, you've added the harmonics. It's become more rich harmonically. And in nature, a lot of sounds are extremely rich in harmonics, which means the tone is never pure. Okay, it's never a pure tone. What you have is you have other tones which are adding up to that one tone to make it sound the way it sounds. All right, so that's where we actually created the sound for the water signal. It isn't just the oscillator that we used. We used the combination then of altering the clarity of the oscillators, okay, which is something called cutoff in synthesis. When you reduce the cutoff, you get a less clear signal. When you increase the cutoff, it becomes more clear. And we increase the loudness so that the clearer the signal, the louder it is, and the higher in pitch as well.
So this is where actually the design comes into play. This is where you're actually designing the sound.
So that's where you're using more complex parameters of the synthesizer to create the sound design, basically, of the signal. In the case of white noise, we still use an oscillator. The oscillator is a white noise generator. Now, if you look at that picture there, it's very different to the waves that you're seeing, the sawtooth and the pulse wave. And what you're seeing there is lots of dots. It's like a television screen which is not working. And that's white noise. Now, white noise covers the whole frequency spectrum between 20 hertz and 20 kilohertz. And what you're hearing is this pulse of all that happening instantaneously. Okay, so if we play the example of noise, it's quite short actually. I thought it was a bit longer. Anyway, you could hear that it doesn't have a tone. It doesn't have a specific frequency like the other two.
It's everything and nothing. It's all tones, all pitches.
Yeah.
All merged.
And that's why it becomes noise, because you're hearing too many tones at the same time. See? So these are the basic building blocks to create the sound, because you need oscillators to create the sound. Without it, you won't be able to do that. Now you can use samples instead of synthesis. So there is a possibility of doing that. And there is a specific method of synthesis called wavetable synthesis, where you're actually using samples rather than oscillators. And then you're affecting the sound using synthesis. But I decided to go for oscillators and try and keep the model working on a simple way so that it wouldn't crash and it would remain as efficient as possible in terms of the RAM of your computer, which has to try and play back the sonification at such a fast speed, you see. So the CPU power involved there. So that was,
of course, that's something we haven't talked about, but of course your CPU has to be able to reproduce these waves, and if they're too complex, that won't be possible.
That's it, yeah. And you see, this is where the sound design is going beyond sound design and going into your interface design as well. It's very important to make it as efficient as possible so that the playback is flawless, that there's no added distortions which are coming from the playback not happening properly, which will actually alter the data. And we know that with digital noise, when your playback is not good, you get extra artifacts of sound, which they will distort the signal. So we wanted to try and avoid that as much as possible.
Of course, you want to have a non-alter sound, which is understandable to the machine and which can be reproduced by the machine, and also understandable for the person who's there, for the scientist who's there telling you, well, this makes sense or not. Because
the problem is, if he suddenly hears a peak that's not there, then you're giving false data. So
yeah, like, oh, I saw something. No, I'm sorry, that's a mistake. You didn't. That's not part of the information. That's just a playback mistake. That can happen.
And it does happen. I mean, I tried to run the model that I built over the weekend, and unfortunately, my CPU was overpowered by a number of different things I was running at the same time, and the playback speed wasn't making it. So you've really got to take these things into consideration. Don't forget, the sonification interface that you're designing is a computer system. Okay, it's a computer interface. It's an application or a software application. So in that case, these factors are going to come into it, and they have to be taken into consideration through the design process as well. So then one final thing we did, we're going back here to the signal, to the effective transiting radii. With the first iteration that I gave the astronomer, okay, I got two aspects of feedback back from him. And one of them was that it sounded more like a mosquito rather than water. So I had to do something about the sound design to make it less irritating at first. But apart from that, he felt that the peaks were not prominent enough. Now, the astronomer I was working with was a non-musical person. And there's a particular effect called the Smark effect. And what do you do? What happens with the Smark effect is that a non-musical person will hear changes in elevation. Okay, so elevation, we're talking about not going from left to right on a flat plane. What we're hearing is the signal stepping up. We hear it as if it's getting higher. And to create this illusion, you need to change the pitch and shift it from the left to the right speaker, to change the timbre and shift it from the left to the right speaker. So we were already doing that, okay? And apart from
that,
that,
in this case, you're enhancing the phenomena. You are not trying to counter the effect, but you're using this this innate. Well, we don't know if it's a problem, but what happens is that when a sound comes from left to right or right to left, you have the tendency of believing that it goes up in pitch.
Exactly. Yeah. Yeah. So it's an audio illusion, basically. It's, you know, when you get visual illusions and you look at a specific, let's say, black and white vortex, and it looks like it's moving because your eyes are trying to calibrate and they can't. So you start getting a slight movement in that thing. This is the same thing. It's an audio illusion where you're hearing something actually going up and not just moving from left to right. So to emphasize the peaks, what we did is we added harmonics. So let's try and explain what that means. So if you're hearing the signal on its own, you're hearing one tone. So we can actually play there. We've got the fundamental frequency. That's one tone playing, okay?
Is that one?
It's the very bottom one where it says fundamental.
Yes, this is the very bottom one. Yes.
Yeah.
Yes.
Okay, so that's your first tone. Now, if you add another harmonic to it, which is your third tone, in musical terms, it would be called your third, but in sound design terms, this goes up in cents, okay? So if you add 400 cents to the fundamental frequency, you get an added harmonic. So now if you play the third tone there, which is where it says third, and you've got a
Oh, let's do it.
So you hear the difference in pitch there between the first and the third?
Yeah.
Now if you play the one next to it, it says first plus third. And you hear a chord.
Yeah, there's a chord with the first and the third, yeah.
Now, from the diagram, what I tried to represent here, hopefully it's clear, the fundamental frequency, as we said, is happening in the left ear. When that fundamental frequency reaches somewhere within the range of 400 hertz, the harmonic so 400 hertz, that signal has moved from the extreme left to somewhere around here on your head, okay? Physically, it's moved as well. And as soon as it's moved to this part, that third tone that you just heard is added on to the first tone. So you hear the two tones together. So you hear that chord, okay? Now, every time that the signal is moving a step up, so over on the fifth added harmonic, which is known as 700 cents, that has now reached the central position in the head. So now we've got the first fundamental, we've got the third because we've gone higher okay, than the first. We've gone up to halfway, we've gone up to about 600 hertz here, and we've added a fifth tone. So if we play that fifth tone now on its own. Okay, that's all three of them together. So
let's just hear the fifth, yeah.
Yeah. That's the fifth on its own. Let's play the first one again.
So you want only the fifth or only the third?
Only the first one, the very first one at the bottom. Okay, now play the fifth again on its own. Do you hear the differences? Boom, boom.
Yeah, absolutely.
If we play all three of them together, we hear
so
that.
First, third, and fifth.
Yeah. So as you can see, what's happening here is that the signal is becoming more rich. You're having more tones added. And this goes on to the seventh. So we've added here 1100 hertz. So we're hearing round about here on the head now. Okay, it's moved, the signal has moved. And you know, if you play these as separate notes, it's going dum, 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 you know, and all the way up. My singing voice is not too good, but anyway. So we've added the seventh, and at the very end, we've added the eighth at the extreme right. So the very large peaks, you're going to hear a whole octave there, plus all the other notes.
So you are not only adding third, fifth, seventh, but you're also changing the pan. You're going towards the right or the left, and it's enhancing.
In this case, yeah, we're going towards the right.
Towards the right, you're going towards the right. You're going high and towards the right. So your experience it's deeper. You feel that it's more clear for you that you're actually going high. You're going higher.
You're going higher, and because of this, because you're hearing that added tone every time, you can tell the difference between the peaks. See, now don't forget what we've played back here are pure musical notes, but I did not use pure musical notes for the sonification. I used frequency. So this stepping up of the chords never sounds the same if the fundamental is not a specific frequency. And usually it wasn't. It was jumping between a range. So this chord is not sounding, you're not going to hear that chord being played over and over again, the one that we just heard.
It's going to change.
It's going to change according to the fundamental note. And that's very important because that helps you to measure the differences between the peaks, see, because you're taking it from the fundamental note and you're hearing it. For example, if you're hearing it less than you heard it the previous time, it means that peak is slightly smaller than the previous one. You see what I mean? So this is what makes it so easier to be able to distinguish these peaks.
But when you get the information, let's say, of the first note, of the fundamental, right? And then you add these harmonics for the ear to better distinguish the fundamental, because it's more complex, it's more rich. So when the fundamental changes on its own, it won't be as clear as changing the whole chord.
That's it. Basically, what's happening is it's stepping out with the noise signal. We're not including the noise signal up until now, but once you hear the sonification with the noise signal on it, you'll understand why these harmonics make it so much easier to hear the peaks.
Why they are needed.
Why they're needed. And what happens as well, you're not just getting a left and right movement. The astronomer had actually described the radii as becoming higher. So he imagined them going like that, not just like that, not flat plane. He imagined these frequencies getting higher, in terms of height. And that's the illusion we wanted to create. And that's what helped him to be able to distinguish the differences in the peaks. So at the very end there, at the bottom of the right-hand side, I've got a small box there saying harmonics added left to right. If you play that back, you'll be able to hear when each harmonic is added, you can hear them being added from left to right speaker. Okay, so that's it. And you feel the sensation of the movement just coming from that. The tones are making it easier for you to hear that movement, basically. So that's basically the sound design that was used for this specific model. So at the very end, once you've designed it, you want to evaluate the model. You want to make sure that it works properly, and it's very important to do that. If you've just designed it and you think it's going to work okay because you've worked with him throughout the process, the astronomer might come along. Astronomers are very busy people, and they'll easily forget all that you've told them throughout the whole design process. So on the day when we did the evaluation, I had to explain, right, yeah, we did the mapping this way, we did it that way. And then I said, right, I want you to play around with it and see if you can hear what it is that you're looking for. Okay. And the astronomer was able to hear this specific water feature that just popped out at around 2 to 3 microseconds in the playback, which caught his attention. And he went back and he listened to it a couple of times and he kept saying to me, I think we found something here. When later he went back to confirm whether we found a water feature, it was confirmed that. So it only took, I think it was about 30, 40 seconds for him to do this. After he played around with the model and familiarized himself with the sonification, he was immediately able to hear this particular characteristic. So you see, the evaluation helps because then what we realized is that we want to see whether the interface was intuitive for the astronomer to be able to use. Did he know how to slow down the time and speed it up? Did he know how to choose segments on the interface to listen to specific parts? How was the sound design? Could he recognize that he was listening to signal compared to noise? Was he finding it hard to hear the differences? Did it sound like what he wanted it to sound? Does it sound like running water? Is it nothing like running water? And from the feedback that you get at this stage in the design process, you can tweak the model to perfect it. That's, you never get it perfect, but to get it as close as possible for him to use without any difficulty. Luckily, with this design, the only changes that were requested were not in the sound design itself. It was only in the interface where I didn't use astronomical measurements. I used line numbers, and he preferred to have astronomical measurements that he could choose 2 to 3 microns instead of line 17,300 or something to 19,000. It's much easier to use the microns, which I didn't realize this, and it was a good point to And even with playback, we wanted to add some tools like a scrub tool where you literally put the player next to the wave, and you can hear that specific part of the sonification without choosing the segments. So there were just tools for speeding up, fast forwarding and rewinding in the playback. Very superficial changes, but the sound design itself, he was very happy with it. So I think at this point we can actually play the final model as it was created with the noise signal on top of the signal.
Absolutely, yeah. Let's. So I'm going to play the water vapor model as you finished it. Well, thank you so much. Before I play, I really want to thank you once more because this has been such an amazing and informative talk. And I like how you really work together hand to hand with the astronomer, and how even in the evaluating step at the final step, it was important for the astronomer to actually being able to loop on his own, to change volume, to just to actually get to know the tool, because I think that that's also important. Well, let's play the final model. So this is water vapor and noise from the atmosphere of an exoplanet. I'm sorry, that was the asteroid at the end.
Yeah.
So you can actually hear that there is more vapor, that there is, you can see how the rhythm goes higher, how the amount of bits increases, and you feel, oh yeah, there is something, there is more here, and the pitch changes. So you feel, okay, it's getting closer, it's getting farther away from me.
That's it. It becomes very intense. The more the peaks rise, the sound really becomes intense, and this is it. It's a signal. So basically, it's working as an alerting system to show you that the peaks are getting higher, and then you can focus on that. Now, if there's a specific peak which caught your attention, you can go back and play back that specific segment and study it in more detail. So one of the techniques is that you can grab that peak and you can slow it down, and you'll be able to hear it in more granular detail. Each of those peaks, each one of them, it consists of a number of different data points. You see, so the peak is built up of individual sounds. When you slow the signal down, you hear it tuk 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 tuk. And instead of whoop, you hear tuk 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 tuk, and you can stretch that. You can make it faster, and there maybe you could hear details which on a graph you won't be able to see unless you can stretch that graph.
Yeah, but then you would need a huge screen or a huge sheet of paper.
Exactly. I mean, this is where maybe from a visual point of view, once you start using virtual reality, you'll be able to go into the virtual world and grab the graph and actually stretch it. But again, you've got to walk away in the virtual world.
Exactly. You've got to zoom out, or you have to walk through it. You cannot really see it at the same time. Yeah.
That's it. You see, so this is where the zooming becomes very micro. It's micro-factored down, so that you can actually hear specific detail, which you won't be able to see. And I think this is where, I advocate sonification, maybe not as a standalone thing, but to work in cooperation with visualization. I think as a final thing, which I'd like to say, you mentioned earlier that sonification could help people who are visually impaired. And there is actually an example of an astronomer whose name is Wanda Diaz Merced, who became blind when she was studying astrophysics at university. And she thought that that would be the end of her career as an astrophysicist. But then she started using sonification and developing her own sonification system, which is called Exonify, to be able to do astronomy. When she lost her sight, her sense of hearing became much more acute. So she could hear much more detail than you and I can, because we depend on our eyes as well. and she uses sonification to do her astronomy. So it's actually a system that can replace visual data. We
Wow.
can see this from the example of Wanda Diasmer said. She has a very interesting TED talk, actually, which if you're interested in listening to, I would suggest that you give it a look, because it's very interesting.